Some microcontrollers actually contain real DACs on board, like the Arduino Due, for example. The Arduino Uno kind of makes up its own version of a digital and analog converter, and the analog write command that you've used in the past controls that particular output. But as you might remember, that output is driving a pulse width modulated, or PWM, signal. And if you remember, a PWM signal looks something like a pulse train, right? So it's a square wave with a non-50%, not necessarily having a 50% duty cycle. So for example, in this case, maybe I have something like a 25% duty cycle for this particular signal. And that's something that I might command with something like analog write. I provide a pin number for a PWM pin on the Arduino Uno, and then 64, because this is an 8-bit DAC, right? So this PWM signal is based on an 8-bit number, and 64 divided by 256 is 1/4, or 25%. So the signal, this digital signal that I have coming out here is going between 5 volts and 0 volts. The timing of it can change a little bit based on whatever commands you actually use on your Arduino, but typically a period on this would be something on the order of 2 milliseconds, for example. So if this was 0, 2 milliseconds, 4 milliseconds as an example. But this is clearly not an analog voltage that we'd expect to get out of a digital to analog converter. This is a pulse width modulated digital signal. So how do we actually get an analog voltage out of this? Well, for this we actually have to cheat a little bit, and we add some external circuitry. In our case, we're going to add a low-pass filter. And so at the input of this filter, I have that PWM signal right there. And then at the output of this low-pass filter, I'm going to get an approximate analog output voltage based on the duty cycle of this PWM signal. And of course, that's assuming that I choose my R and C correctly to filter that. So I have an R and a C. And those give me a time constant, tau is RC here. Of course, I could also think of that as having some corner frequency for my filter of 1/RC. Right? And so based on the frequency of this PWM signal, I'll want to choose my R and C so that I get a filtered version of this signal. And by that filtered version, I mean something that's kind of charging and discharging, and it'll settle on a level that's, approximate, in this case, 1/4 times 5 volts. So in our case, it'll be around 1.25 volts here. But it's going to be charging and discharging that capacitor each time, so it has a fair amount of ripple associated with this particular signal. So it's definitely not a flat line that I might want out of a digital to analog converter. Now, to minimize that ripple, I can either increase the time constant of my circuit, or I can increase that PWM frequency. Either way, I'm slowing down the corner frequency of my filter relative to the frequency of my PWM signal, right? I want this attenuated. Of course, the challenge with doing this is that increasing tau is going to increase the DAC settling time, or effectively the time that it takes to reach a newly commanded voltage. So if I switch from analog write 364, and then I go to analog write after some delay, say 128, right? 128 should put me at about 2.5 volts instead. Having a large time constant or a low corner frequency with this filter, it'll take a long time to move from 1.25 up to 2.5. So that's just one way to approximate a digital to analog converter on a microcontroller that would give you a pulse width modulated output, which almost all of them do. Right? I need 2 external components to create my RC filter, and I can create an approximate analog voltage. Right? I need some kind of filter on that output some kind of low-pass filter on that output in order to be able to get my approximation of the analog voltage. But if I have that filter, I can get something close. Another way to create a DAC using some digital outputs is to use a summing amplifier circuit. So I have my V out here, I have a negative feedback path with a resistor R in that path, and then I have a couple inputs here. So I'm going to call this input D0 times my full scale range, and this one D1 times my full scale range. And D0 and D1 in this case are going to be binary inputs. So I can either have 0 volts at this input or my full scale range voltage at this input. So this example I'll also say is a 2-bit version of this DAC. It's a little easier to go through the analysis, but I can create even more bits to this DAC by adding more resistors, and I'm going to multiply by 2 each time. So I'm going with R, 2R, 4R, 8R, and in this case my D0, my least significant bit term, is always going to be at the highest resistance. So in this case I'd have D0 there, D1, D2, and D3 in a 4-bit version of this DAC. But I'm just going to analyze the 2-bit version here. In this case we have ground attached to our non-inverting input of our op amp, and then we have a virtual ground, of course, at this inverting node here. So then it just comes down to doing KCL on the resistors. So if I define my currents as IRF for the feedback path, IR for the current going through the R resistor, I2R going through the 2R resistor, I'm going to use KCL. So I know all of those nodes are going to sum to 0. So now I can start just writing out the expressions for these various currents. I'm actually going to change this. I'm not going to make this VFSR because I think that will be confusing in the end. I'm just going to call that some kind of V supply. So say that's 5 volts or 2.5 volts or something. It could be some arbitrary number, and we'll have some factor of that will ultimately be the full scale range of the DAC. So in this case I can have 0 volts or VS volts at each input. So if I start writing out these expressions, I get this, and I can multiply by 2R, and finally I'll get a V out that's minus 1/2 times 2D1 plus D0 times that voltage. And I can look at what kind of V out I'm going to get for my different combinations of digital inputs here. So I can have 0, 0, 0, 1, 1, 0, 1, 1 at my input, and my V out, if both are 0, I'm going to get 0 volts at my output. If D0 is 1 and D1 is 0, then I'll get minus 1/2 of VS, so minus VS over 2. If this one's 1, I'll get minus VS, and then finally if both are 1, I'll get minus 3 VS over 2. So remember before, our generic kind of output from a DAC would be something like V out times the code over 2 to the m, where m is our number of bits, times some full scale range here. So this will hold if VFSR is defined as minus 2 VS in this particular case. So if I had a code of 3 here, I'll have 3/4 times minus 2 VS, which is minus 3 VS over 2, which is what I get here. All right, so while the implementation is a little more complex, this is going to get you a nice steady output voltage versus that RC filter approach with PWM. So final topology that I'll talk about for making a DAC is called an R2R DAC. So that previous summing amplifier, one of the nice things is that I don't need so many resistors, but I need R, 2R, 4R, 8R, 16R, right? And ultimately I'm getting this very large range of resistances, which can often be hard to find. In this case, I only need one resistor at R, and a bunch of resistors at R, and a bunch of resistors at 2 times that. So I'll start with the 2-bit version of this again, and then show you how you would extend this to more bits. So in this case, other than the resistor to ground, which is 2R, I have 2R resistors up to my digital inputs and R's in between them. So in this case, I have my least significant bit, digital input, is the closest to that ground terminal there, going through that 2R, and D1 times some VS, right, where D0 and D1 are digital inputs. They're binary again, 0 or 1. D1 times VS is going through this 2R, and then I'm defining my V out at this node right here. If I wanted to keep going and make a higher bit count, higher resolution DAC, I could do something like this for a 4-bit DAC. So in that case, I still have D0, D1. Now I'd have D2 VS and D3 VS here as well, and my V out now would be at this node, and these would still be 2 R's going up to those digital inputs and R's between those. So I'm going to once again analyze the 2-bit case. So I'm going to define a voltage node right here, VA, and then I'm just going to do my KCL once again. So I'll start with these two currents right here, D1 times VS minus V out over 2R is equal to V out minus VA over R. And ultimately I get 3 V out is D1 times VS minus 2 times VA. So now I need to figure out VA. I'm going to use these currents right here. And I can just plug this back in here, and I just realized this should be a plus sign over here. I'm moving that over on this side. So ultimately I'll get 3 V out is equal to D1 VS plus D naught VS over 2 plus V out, or V out is equal to D1 over 2 plus D naught over 4 times VS. So this is the output of my R2R ladder DAC. This is often called a ladder DAC because it looks like a bunch of rungs on a ladder. So once again, if I want to look at what my actual output voltage is for different combinations of digital inputs, I have D1, D naught, and my V out here. If both are 0, I'm going to get 0 volts. D naught is 1, I'll get VS over 4. Similarly, VS over 2, and 3 VS over 4, sorry. Right, so this also matches up with the output that we talked about earlier of getting your code over 2 to the M times, in this case, our VFSR is VS.